Hello there, and welcome back to Fall Asleep to Astronomy. I'm glad you've slipped into this little pocket of quiet with me tonight. Outside, the universe is unhurried, planets circling in the dark, stars keeping their patient watch, while in one small corner of space, we turn our attention to a red world we've wondered about for generations. Tonight, we'll drift toward Mars and the echoes of its ancient seas. New images, carved in light and dust, hint at shorelines long gone and patterns in the rocks that make scientists whisper the same question you might be holding now. Could something once have lived in those vanished oceans? We won't rush for answers. We'll move slowly, like a telescope gliding across the sky, letting each detail arrive in its own time. If this gentle stargazing feels like good company, a soft like and quiet subscribe. Help others find their way here too. When you're ready, we'll wander into the story together, unhurried and warm. Mars, the small red lamp in our night sky, has been tugging at our imagination for longer than we can remember. It looks so quiet from here, just a faded ember among brighter stars. Yet every new photograph sent back by orbiters and rovers whispers that it is far richer, far more complicated than we once believed. With each fresh image, the planet seems to lean a little closer, revealing just enough to keep us wondering, never quite enough to fully understand. When we look at those pictures, what we see is not just rock and dust. We see old stories frozen in place. There are dry riverbeds etched into its rusty skin, like the empty paths of streams that once laughed their way across the surface and then simply stopped. We see gentle curves that look like shorelines with no water, basins that resemble the bottom of vanished lakes, and smooth plains that feel like the ghost of an ancient sea floor. High above, delicate clouds curl and stretch, drifting through the thin Martian air, hinting at invisible motions and quiet cycles still at work. All of these features are like scattered pieces of a puzzle that was knocked over a very long time ago. When we place those pieces side by side, a picture begins to emerge. A Mars that was once warmer, wetter, more alive with motion. A Mars where water may have flowed freely over the landscape, filling valleys, pooling in depressions, carving gentle paths through soft soil. It is a strange feeling to realize that the planet we know as dry, cold, and almost airless might once have sounded more like rain than like dust. And of course, when we think about water, our minds move almost automatically to life. Even the smallest idea of an ancient ocean on Mars feels like a door opening in the dark. Could there have been microbes drifting in those long-vanished seas? Tiny forms of life clinging to rocks near warm springs, hiding in sediments, or resting in mineral-rich mud? We do not know, but the possibility is enough to keep telescopes pointed and rovers rolling. Then there is the other question that always waits in the background. Not just whether life ever called Mars home, but whether we might one day do the same. Mars is harsh, but not unreachable. Among all the worlds we can see, it still seems like the next most plausible address for our species, the most likely place where distant descendants of ours might look up at a pale blue dot in the sky and call it home. Even the great volcanoes on Mars feel like characters in this quiet story. Olympus Mons, the colossal shield volcano towering above the surrounding plains, has long been considered dormant, a sleeping giant that has not stirred for millions of years. Yet some research suggests that it may not be entirely finished with its work. If Mars still has a warm, restless heart deep below, still reshaping itself in small, slow ways, then the planet is not just a relic. it is a place still in motion. For future explorers, that matters. A geologically active world might offer both risks and gifts. Quakes and changes, yes, but also heat, minerals, and hidden pockets where water and chemistry continue their long, patient conversation. New images keep arriving, and they are changing the way we think about Mars as both a memory of a wetter past and a canvas for future journeys. A research paper published in the middle of this year added another layer to that evolving picture. It gathered together lines of evidence about water on Mars, helping us look both backward into its ancient history and closely at its present state. The story that emerges is simple at first glance, yet deeply unsettling. Mars, that cold and desolate world we see now, appears to have once been warm and wet, with extensive bodies of water spread across its surface. Lakes, inland seas, maybe even something close to an ocean. Now, when we look, we find a landscape that feels almost abandoned. Thin air, low temperatures, dust storms instead of rainstorms. The natural question rises like a quiet echo. If there was so much water, where did it all go? To approach that question, scientists turned not just to pictures of the surface, but to the fragile blanket of air above it. A joint study, using the Hubble Space Telescope and NASA's Mars Atmosphere and Volatile Evolution mission, focused on how the planet is losing water today, right now, as it moves around the Sunday. What they found is that Mars is not just dry, it is actively leaking what little water it has left, and it does so in a way that changes with the seasons. As Mars travels along its slightly stretched out orbit, there is a point where it draws closer to the Sunday. This point is called perihelion, and at this part of its journey, the planet receives more solar energy. Its thin atmosphere warms noticeably, even if the surface still feels bitterly cold by earthly standards. That increase in atmospheric heating has a subtle but powerful effect. It allows more water vapor to rise higher into the air. The study showed that around perihelion, the concentration of water vapor in the upper atmosphere increases, and with it, the rate at which hydrogen and deuterium escape into space. In the colder, more distant part of the orbit, called aphelion, this escape still happens, but at a much calmer pace. Near perihelion, however, the leakage can increase dramatically, sometimes by a factor of 10 to 100, compared to the quieter times farther from the Sunday. It is as if the planet briefly opens small windows and lets its remaining water slip out into the dark. John Clark of Boston University described the Martian atmosphere as being very turbulent, heating up and cooling down on short timescales, sometimes changing its behavior within hours. During these warmer seasons, water vapor that would usually stay closer to the ground can reach higher altitudes. Once it is up there, under the harsh gaze of the sun, something delicate happens. Solar ultraviolet light strikes the water molecules, splitting them apart into hydrogen and oxygen. Hydrogen, being very light, can escape Mars's weak gravity if it is given enough energy. It simply drifts away, lost to space. Oxygen is heavier and more likely to stay behind, but it does not remain as a free gas for long. Instead, it reacts with the materials in the Martian soil, binding itself into minerals and leaving behind that familiar reddish tint that gives Mars its color. Over countless years, this slow, quiet process has been peeling water away from the planet, molecule by molecule, until only traces and memories remain. There is another clue, tucked into the chemistry of the atmosphere itself. Not all hydrogen atoms are the same. Some are slightly heavier because they contain an extra neutron. This heavier form is called deuterium, When water breaks apart and hydrogen escapes to space, the lighter hydrogen gets away more easily than deuterium. Over billions of years, this selective escape changes the ratio of deuterium to ordinary hydrogen. Mars ends up with relatively more of the heavier kind left behind. By measuring this ratio, scientists can look backward in time, the way one might look at the rings of a tree to guess its age and the conditions it lived through. On Mars, the deuterium to hydrogen ratio is now about 8 to 10 times higher than what we find on Earth. That is a quiet but powerful hint that enormous amounts of water must have been lost over the ages. The present atmosphere carries the chemical accent of a world that once had far more to drink. And yet, even after all this loss, the story is not simply one of emptiness. Mars still holds on to significant reserves of water, though not in the open lakes or seas we might imagine. Most of it is locked away as ice, hidden in polar caps and buried beneath layers of dust and rock. Some may be trapped in minerals. Some may sit in deep underground reservoirs where sunlight never reaches. When researchers run the numbers, they find that if all the known and suspected water were somehow melted and spread across the planet, it could form a global ocean several kilometers deep. That image alone is enough to renew hope and curiosity, suggesting that Mars is not just a place that used to have water, but a place that, in its own quiet way, still does. While scientists trace the story of water, another mystery has been unfolding high above the Martian surface, one that may be tied not just to geology and climate, but possibly to life itself. This mystery centers on a simple molecule, methane. On paper, methane is nothing more than one carbon atom bonded to 4 hydrogen atoms, an unassuming bit of chemistry. But on Mars, it behaves like a whispered rumor that will not quite go away. Methane has been detected in the Martian atmosphere in short, surprising bursts. These bursts are small compared to Earth's thick air, but on a planet as thinly veiled as Mars, they stand out. NASA's Curiosity rover first noticed a significant rise in methane levels in the period from late 2013 to early 2014, measuring concentrations roughly 10 times higher than its usual background readings. Since then, Curiosity has recorded several similar spikes, most often during the late spring and early summer of the Martian year. This gentle seasonal pattern suggests that something on or within the planet is breathing methane out in a way that changes with time. The puzzle is figuring out what that something might be. On Earth, much of the methane in our atmosphere is created by living things, especially tiny microorganisms known as methanogens. These microbes thrive in places without oxygen, feeding on simple chemicals and releasing methane as a byproduct of their metabolism. It is tempting to look at the Martian methane and imagine something similar hiding there, far from the surface. But modern Mars is a harsh host. The surface is cold, bathed in radiation, and almost completely dry. There is no stable liquid water in open view, only ice and brief, fragile films that may form and vanish quickly. That makes life, as we know it, on the surface, very unlikely. The idea that remains is quieter and more hidden. If life exists on Mars, it might be tucked away below the surface, in tiny cracks and pores where liquid water can still persist. Down there, the pressure is higher, the temperature may be more forgiving, and rock and water can share long contact. Some models suggest that microscopic pockets of water could saturate parts of the crust, creating small, sheltered environments where chemistry and perhaps biology can continue unobserved. Even without life, there are known pathways for methane to form. One possibility involves liquid water interacting with minerals rich in iron and magnesium, such as olivine. On Earth, Similar reactions can produce hydrogen gas when water seeps through certain types of rock. Once released, that hydrogen can react with carbon dioxide through a process known as Fischer-Tropsch type synthesis, creating methane. If something like this is happening beneath the Martian surface, then the methane we see might be entirely geological in origin, a natural outcome of rock, water, and time. But here too, Mars complicates the story. The planet is not as geologically active as Earth. Its crust does not churn with plate tectonics, and its volcanoes, as far as we can tell, have been mostly quiet for a long time. That makes it harder to explain why methane levels would jump quickly and then fall again, as curiosity has observed. The bursts seem too lively for a world whose interior is thought to be so calm. This tension between slow geology and rapid observations has led some scientists to circle back to the idea of methanogens. Perhaps, they suggest, tiny organisms deep underground could be consuming hydrogen and producing methane as a metabolic byproduct, breathing in the dark and sending faint chemical signals upward. It is an enticing thought, an almost cinematic image of life hanging on in hidden reservoirs, far from the biting cold of the surface. Yet for now, that is all it is, a hypothesis, a careful maybe. No direct evidence of life, no fossil microbes, no clear biological fingerprints have been found. The methane itself also presents another challenge. On Mars, it appears to break down faster than we would expect. Methane is not particularly stable, but under normal conditions it should linger in the atmosphere for a long time. Instead, observations suggest that something is destroying it fairly quickly, perhaps through ultraviolet light from the sun, or through reactions with dust and oxidizing chemicals in the air and on the surface. Taken together, these clues point to a deeply complex interplay of environmental factors. Water rises and escapes, hydrogen drifts away, deuterium builds up, oxygen stains the soil, methane appears, grows stronger, then fades, touched by sunlight and chemical reactions we do not yet fully understand. Mars, which once seemed straightforwardly dead and simple, now looks like a place where many subtle processes are woven together. For all our orbiters, rovers, and telescopes, there is still so much that remains out of reach, locked beneath rock and ice, or hidden in whispers of gas too faint to fully decode. The patterns we have found so far remind us that we are only beginning to listen properly. And even now, with all that we know, we still have much more to learn about what lies beneath the surface of the planet itself. While so much of Mars keeps its secrets buried under rock and ice, another part of its story is written high above, in the thin air that wraps the planet like a fragile veil. That atmosphere is cold and delicate, almost weightless compared to Earth's, and yet it puts on a quiet show for anyone patient enough to watch. Clouds bloom and drift there, changing shape and flowing across the sky in ways that feel strangely familiar, like watching weather from home, and at the same time, unmistakably alien. For the past 2 decades, the European Space Agency's Mars Express spacecraft has been keeping a gentle eye on these shifting patterns. Orbit after orbit, its cameras have collected countless images of hazy veils, curling plumes, and soft streaks of cloud sweeping over dusty plains and towering volcanoes. Taken together, these pictures have given us the most detailed glimpse we have ever had of Martian weather, a theater of storms and mists that looks almost earthly at a glance, until you remember just how different that world really is. This year, scientists at the German Aerospace Center gathered thousands of those images and stitched them into something like an atlas, a guided, immersive tour through the clouds of Mars. It is not just a catalog of pictures, but a way of wandering through the sky of another planet, watching how its clouds form, stretch, and dissolve over time. In their quiet way, these moving shapes tell us how energy and matter flow through the Martian atmosphere, how sunlight, cold ground, and complex winds weave together to create patterns in an air so thin you could almost forget it is there at all. On Earth, we are used to clouds made mostly of water vapor, with droplets and ice crystals forming in a relatively dense blanket of air. Mars is different. Its atmosphere is dominated by carbon dioxide, and it is so rarefied that whatever traces of moisture exist are spread out like mist through a cathedral, faint and fragile. The total amount of water available is incredibly small, thinner than a strand of hair when compared to the ocean of moisture surrounding our own world. And yet, despite that scarcity, clouds still manage to form, sometimes in ways that take even seasoned scientists by surprise. One of the most striking examples is a recurring giant, an elongated cloud that appears near one of the great volcanoes of the southern highlands, a mountain called Arsia Mons. This feature is often shortened to the Arsia Mons Elongated Cloud, or AMC, a ribbon of brightness that unfurls in the morning sky each spring. It is made of water ice, not volcanic smoke, and it rides the winds that sweep up along the volcano's vast slopes, rising to high altitudes where the air is frigid enough for the faint moisture to condense. What makes this cloud so remarkable is its sheer scale. At its largest, it can stretch for roughly 1,100 miles, a delicate feather spanning a distance greater than many countries on Earth. It can also move at impressive speeds, racing along at up to 370 miles per hour, all while remaining anchored to the region around the volcano. From orbit, it looks almost like a luminous trail being pulled out behind the mountain as Mars rotates beneath the sunday. Because it appears so close to a volcano, the cloud might easily be mistaken for a sign of eruptions or hot plumes rising from deep within the planet. But careful study has shown that this is not the case. There is no smoke, no ash, no fresh lava. Instead, the AMC seems to be born from the way air flows over the terrain, from the shape of the land itself, and the way morning sunlight wakes the atmosphere. It is a product of wind, temperature, and topography, combining in just the right way, a natural painting brushed by invisible currents rather than by molten rock. And this is only one kind of cloud that Mars can make. The planet's atmosphere supports an entire family of formations, each with its own personality. There are cloud streets, long linear rows of puffy clouds that march across the sky in parallel lines, very much like certain kinds of cumulus clouds we see over Earth's oceans and plains. On Mars, these cloud streets often appear in low-lying regions near the poles, in places such as Vastistas Borealis, and around volcanic giants like Olympus Mons and Arsia Mons, where the landscape gently nudges the air into organized patterns. At a glance, these clouds can look comfortingly familiar, like weather photos taken from our own satellites, yet the conditions that give rise to them could hardly be more different. On Earth, clouds grow in a thick, water-rich atmosphere where droplets condense from air that is already heavy with moisture. On Mars, the air is so thin that even small changes in temperature can tip the balance, turning a nearly invisible trace of water into a visible cloud almost abruptly. A gentle cooling or a local wave of uplift can be enough to coax ice crystals into existence, then let them vanish again as the air shifts. The thinness of the Martian atmosphere also allows for more delicate, unusual structures shaped by gravity waves in the air, not the cosmic gravitational waves that ripple through space-time, but atmospheric waves created when air is disturbed and tries to settle back into balance. When winds blow over mountains or encounter sudden changes in temperature, the air can begin to oscillate, rising and falling in a layered rhythm. These oscillations can produce rippled, ridge-like clouds, stacked like soft furrows across the sky, similar to lee waves seen downwind of mountain ranges on Earth. On Mars, under that pale, copper-tinted light, they look like fingerprints of invisible motions. By watching how these clouds form and fade under such extreme conditions, scientists refine their understanding of planetary atmospheres in general. Every plume, streak, and ripple is a clue to how heat is transported, how dust and moisture move, how seasons breathe in a world so different from our own. Studying Martian clouds is not just about appreciating their beauty. It is about learning the language of climate on a planet with almost no air to spare. Yet the quirks of Mars are not confined to the sky. Beneath that thin atmosphere, on and just below the surface, another strange phenomenon appears, one that looks almost alive at first glance. In the southern polar regions, particularly noticeable during the transitions between seasons, the landscape becomes decorated with dark, branching shapes that spread out across the ice and ground. They look like enormous spiders pressed into the surface, or the exposed roots of some unseen tree. Intricate, web-like forms reaching out in all directions. These features are known by a gentle formal name, areneiform terrain, from a word that means spider-like. They were first spotted by orbiters in the early 2000s, puzzling everyone who saw them. The patterns stretch across vast portions of the southern polar landscapes, sprawling over the ground in complex, branching networks. From orbit, they seem to be drawn there on purpose, as if something beneath the surface were pushing its way out, making marks on the skin of the planet. For a time, their origin remained uncertain, but new experiments carried out at NASA's Jet Propulsion Laboratory and described in a study published this September have brought a much clearer picture into focus. The conclusion is both surprising and oddly satisfying. These spiders are not created by any kind of living creature, but by the behavior of carbon dioxide, ice, and gas under Martian conditions. They are geology and climate working together, acting out a slow, repeating drama each year. Mars's atmosphere, made mostly of carbon dioxide, experiences dramatic swings in temperature between winter and spring, especially near the poles. During the long, cold winter, carbon dioxide from the atmosphere freezes directly onto the ground, building up a layer of dry ice that covers the surface like a seasonal skin. Dust becomes trapped within it, light is scattered through it, and beneath it, the ground waits in darkness. When spring arrives and sunlight returns, the story takes a twist that does not happen in quite the same way on Earth. The dry ice does not simply melt into liquid and then evaporate. The pressure and temperature on Mars rarely allow for that. Instead, the carbon dioxide ice undergoes sublimation. It skips the liquid phase entirely and changes directly from solid to gas. This transformation begins at the bottom of the ice layer, where the surface below warms just enough to coax the solid into gas. As the ice sitting on top is still cold and solid, the newly formed gas cannot escape easily. It builds up in pockets beneath the ice, pressing outward and searching for weaknesses. The pressure slowly increases, like a held breath under a frozen lake. Eventually, it finds cracks, thinner regions, or small openings where it can burst through. When it does, it does not leave quietly. The trapped gas rushes upward, carrying dust and darker material with it, shooting jets into the thin air and carving channels in the underside of the ice and in the ground below. When the gas finally escapes, it leaves behind a branching network of channels that resemble the legs of a spider radiating from a central point, stained by the darker material that has been dragged along and deposited. Some of these patterns can extend for more than a kilometer, with hundreds of delicate branches spreading away from the eruption sites. To test whether this explanation truly matched what happens on Mars, scientists at Jet Propulsion Laboratory recreated the process in a carefully controlled environment using a device nicknamed the Dusty Camera. They placed simulated Martian soil inside a chamber, cooled carbon dioxide until it formed a layer of dry ice on top, and then gently warmed it. As the ice turned to gas from below, the gas erupted through the dusty surface in sudden jets, leaving behind spider-like patterns almost identical to those seen on the southern polar regions of Mars. The experiment provided strong support for a model long proposed by researchers, confirming that these eerie shapes could arise naturally from the behavior of carbon dioxide ice under Martian conditions. This process appears to be unique to Mars because it depends so heavily on carbon dioxide, acting as both a major atmospheric gas and a seasonal surface frost. On Earth, water ice performs many of our polar tricks, but our atmosphere does not lay down thick blankets of frozen carbon dioxide each winter and then rip them open with jets of gas in the spring. The spiders of Mars are signs of a cycle that belongs almost entirely to that world, a rhythm of freezing and sublimation that writes its signature into the ground. Beyond their unsettling beauty, these formations tell a deeper story about climate and time. The distribution of araniform terrain is not random. It is concentrated in particular regions near the South Pole, hinting that very specific combinations of temperature, surface composition, and seasonal light are required for them to form. That pattern may reflect how Mars's atmosphere and climate have changed over long stretches of history, recording where conditions have repeatedly favored this strange dance of ice and gas. By mapping where these features appear and how they evolve, scientists can piece together clues about the carbon dioxide cycle on Mars, how thick its seasonal ice layers grow, how quickly they vanish, and how energy moves between the surface and the atmosphere. Slowly, the spiders become more than just curiosities. They become data points in a broader picture of a changing world. The spiders of Mars are reminders that even in a place that looks still and silent, powerful forces are always at work. Under a thin sky and over ancient rock, carbon dioxide freezes, cracks, and escapes, reshaping the surface grain by grain. These quiet, alien patterns reveal the strength of a climate that does not sleep, a climate driven by cycles. We are only beginning to understand forces that continue to shape its landscape with each passing season. Beneath the thin air and the restless clouds, another story is unfolding inside Mars, quieter and deeper than anything we can see on the surface. For a long time, many people pictured the red planet as geologically asleep, a world whose volcanoes had gone silent, whose rocks had cooled, whose interior no longer stirred. But the more carefully we listen, the more it seems that Mars is not entirely done moving. Far below its dusty plains, there are hints of heat and slow motion that refuse to fade. New data from orbiting spacecraft, combined with the faint tremors recorded by NASA's InSight lander, suggest that something large is happening under one of the planet's most dramatic regions, the volcanic highlands, known as the Tharsis area. This is the home of Olympus Mons, the previously mentioned giant that rises roughly 13.6 miles above the surrounding plain, making it the tallest volcano in the entire solar system. Its size is almost impossible to hold in your mind at once, a mountain so broad and high that it curves gently away beneath you. Yet, as impressive as its visible bulk is, the real mystery lies underneath. Fresh gravity maps of Mars, created by carefully tracing how spacecraft speed up and slow down as they fly over different regions, have revealed a huge plume of magma, a vast, slowly rising column of molten rock hidden beneath Tharsis. This plume stretches for more than 1,000 miles across and reaches deep into the planet's interior. It is like a great, glowing root of heat and liquid stone, pushing gently upward through the mantle, tugging on the crust above. This molten reservoir is not just a pool of hot rock. It is a store of energy and motion that suggests Mars is not as geologically calm as we once assumed. For millions of years, Olympus Mons and its neighboring volcanoes, Ascraeus Mons, Arsia Mons, and Pavonis Mons, have appeared dormant, their flanks carved only by ancient lava flows and dust, with no fresh eruptions in sight. The discovery of such a large, rising plume beneath them naturally leads to a quiet but haunting question. Could these giants be preparing, however slowly, for new activity? Researchers studying the data describe the mantle plume beneath the Tharsis bulge as rising in a steady, almost patient way. It is not rushing upward like a sudden eruption, but drifting, bringing extra heat and partially molten rock closer to the surface over long spans of time. Even if no immediate eruption is expected, this kind of gradual movement hints that Mars's interior is still warm enough and dynamic enough to drive geological change. The planet, it seems, still has a heartbeat. The way we know this is through subtle variations in gravity, measured from orbit. Where there is a large mass of dense rock beneath the surface, a spacecraft passing overhead feels a slightly stronger pull. Where the material is lighter and less dense, such as a vast basin of magma, the pull is slightly weaker. Over Tharsis, the pattern of these gravity anomalies reveals pockets where the force is diminished, pointing to a large, less dense magma basin hidden below. These quiet discrepancies tell us that Mars's internal structure is more tangled and varied than the simple, cooled shell we once imagined. The rising plume under Tharsis is not just about Olympus Mons alone, either. It concerns the entire volcanic system that covers this region. The Tharsis bulge itself is enormous, a plateau some 3,000 miles wide and roughly 4 miles high, with volcanic peaks scattered across its surface like islands on a raised sea. As the mantle plume continues its slow ascent, it could feed localized volcanic events in parts of this plateau that have not seen lava in countless ages, gradually redrawing the landscape in subtle, patient strokes. It is natural to wonder why such a plume would be rising now, after such a long period of apparent stillness. According to current theories, mantle plumes take shape over millions upon millions of years, forming as hotter, buoyant material from deep inside the planet gathers and begins to rise. Mars's internal dynamics, its cooling core, its stiffening mantle, its long thermal history, may have shifted just enough to let this particular plume climb higher, pressing against the underside of the crust. If Mars is still geologically active in this way, the implications reach beyond lava and mountains. A planet with internal heat can potentially sustain liquid water below the surface, even when the ground above is frozen and dry. Warm pockets near volcanic regions could host aquifers or thin films of water hiding in rock fractures, sheltered from radiation and sharp temperature swings. For the search for life, this matters more than almost anything else. Liquid water, protected underground and warmed from below, is one of the most promising ingredients for habitability. That makes the Tharsis region, with its ancient lava flows and signs of deep internal heat, a particularly tempting place to study. In its rocks, in its fractures, and in the minerals laid down by long cooling magma, there may be clues about past environments that were more welcoming than the surface appears today, and perhaps hints of present-day chemistry that still has room for life, even if only in the most modest and hidden forms. While scientists are carefully unraveling these deep interior stories, Mars continues to offer smaller, almost playful surprises on its surface. Little details that catch the eye and, sometimes, carry serious scientific weight behind their charm. One of the more recent finds is something that looks disarmingly simple: a smiley face traced onto the dusty skin of the planet. This face was captured by the European Space Agency's ExoMars Trace Gas Orbiter, and at first glance, it really does look like an emoticon, carved at planetary scale, a curved mouth and two round eyes set into the red terrain. But beneath the whimsy, there is a quieter significance. This feature is actually the remnant of an ancient lake that dried up billions of years ago. The arc of the smile is made from deposits of chloride salts, arranged in such a way that the human brain cannot help but see a grin, while the eyes are impact craters left by meteorites. What truly drew scientists' attention was not the playful shape, but the material itself. Chloride salt deposits form when water once stood, then slowly evaporated, leaving behind a crust of minerals that record its presence. The fact that these salts remain on the Martian surface tells us that long ago, liquid water pooled here long enough to concentrate and crystallize these materials. This fits into the broader picture we have been drawing: a Mars that once had lakes, rivers, and perhaps even shallow seas before its climate shifted into the cold, thin-aired world we see today. Comparisons with Earth suggest a likely cause. Our planet is protected by a magnetic field that shields the atmosphere from the full force of the solar wind. Mars appears to have lost most of its global magnetic field very early in its history. Without that shield, its atmosphere was gradually stripped away, thinning over time. As the air pressure dropped and the greenhouse effect weakened, liquid water could no longer remain stable on the surface. It either froze, seeped underground, or was lost to space. What remained were traces, dried lake beds, carved channels, and salt deposits, like the ones that make up the faint smile on the Martian plain. Scientists speculate that these ancient salt-rich sediments might have done more than simply remember the water. On Earth, salts can preserve biological material for astonishing lengths of time, protecting it from decay. They can trap tiny bubbles, films of brine, and even the remains of microorganisms. If microbial life ever existed in those Martian lakes, its traces might still be nestled within the salt crystals, sheltered from radiation and erosion. The smiley feature, then, becomes more than a cosmic coincidence. It becomes a possible archive. Because of this, chloride deposits are seen as ideal targets for future missions. They offer a combination of clear evidence of past water and a natural ability to preserve delicate structures and molecules. Instruments carefully designed to sample and study salt-rich layers might one day sift through these ancient sediments, searching for chemical fingerprints that cannot be produced by geology alone. In the quiet stillness of these deposits, the story of ancient Martian life, if it ever existed, could still be waiting. Mars also continues to send back images that tug at something soft and human in us: the need to see ourselves from far away. In one especially memorable picture, NASA's Curiosity rover managed to capture Earth and Mars's moon Phobos in the same frame. It is a simple scene, just a tiny pale dot, our home, sitting near the darker presence of the larger Martian moon, but it carries a strange, gentle weight. Seen from the surface of Mars, Earth is no more than a small point of light, a distant glimmer hanging in the sky beside a moon of another world. Everything we know, everyone we love, every story we remember is compressed into that tiny speck. Phobos, rough and irregular, appears nearby, a reminder that we are looking out from a place where the familiar has become foreign, and the foreign has become the everyday sky. Images like this reshape our sense of distance. Millions of miles lie between those worlds, yet a single camera can hold them both at once. They remind us that while the space between planets is vast, it is also bridgeable by light, by radio signals, by machines that roll slowly across alien ground. Each new photograph, each new map, each quiet measurement is another thread woven between our world and Mars. As exploration continues, the red planet will keep offering more of these moments. Breathtaking views, subtle clues, and discoveries that change the way we think about geology, climate, and the possibility of life beyond Earth. There is every reason to expect more images that make us pause, and more findings that gently shift our understanding. And while we wait for the next rover drill to turn, the next orbiter to send back its data, there is a kind of comfort in simply following along, letting the story of Mars unfold, step by quiet step, and allowing ourselves to remain softly, steadily curious. Out beyond Mars, far past its dusty skies and quiet volcanoes, there is a different kind of mystery waiting in the dark. It is not a single planet or star, not something you could point to with a finger and say, "There it is." Instead, it is more like a deep, slow current in the ocean of the universe itself, an invisible tug that has been pulling on entire galaxies for a very long time. Hidden behind the bright band of the Milky Way, in a region of sky astronomers sometimes call the zone of avoidance, because our own galaxy's dust and stars block the view, lies a vast gravitational anomaly. It is so immense, so powerful, that it tugs on the motions of galaxies hundreds of millions of light years away, including our own Milky Way. Astronomers gave it a name that sounds almost like a storybook title: the Great Attractor. The strange thing is that we cannot see it directly. Through ordinary telescopes, the region looks crowded with the foreground glow of our own galaxy: dust clouds, star clusters, glowing gas. Yet when scientists measure how galaxies are moving, they find that something massive is pulling on them, gently but firmly changing their paths. It is as if we are watching leaves floating on a river and realizing there must be a hidden whirlpool ahead, even though the water's surface looks calm. Naturally, this raises all kinds of questions. Is the Great Attractor a single enormous object, like a supermassive black hole larger than anything we have ever seen? Is it a huge cluster of galaxies packed together more densely than usual? Or is it not one object at all, but a region where a great deal of mass, both visible and invisible, has gathered in a vast knot of gravity? And behind those questions lies a quieter one. What does this mean for us, for our galaxy's journey, and for the way we understand the future shape of the universe? The story of the Great Attractor, at least for us, began only a few decades ago. Around 40 years back, astronomers used the Parkes radio telescope in Australia to peer through some of the dust that usually hides parts of the sky. By studying the motions of many galaxies, they realized that our Milky Way is moving through space faster than they had expected. Not just drifting, but really plunging, as if drawn towards something unseen. To picture that motion, It can help to think in comparisons rather than bare numbers. Imagine the cruising speed of a passenger airplane, the way it hums steadily across the sky. Now imagine our entire galaxy moving at a speed thousands of times greater than that. The Milky Way's motion is also dozens of times faster than the escape velocity from Earth, the speed a rocket needs to break free of our planet's gravity, and even roughly twice the speed a star would need to escape the gravity of the galaxy itself. It is not a gentle shuffle. It is a determined glide. According to the basic picture from the Big Bang, space itself is expanding on large scales. Every galaxy should be moving away from every other, like dots on a balloon as it inflates. Galaxies on either side of us should show roughly the same kind of recessional motion, their speeds mostly explained by this cosmic expansion. In that simple view, there should not be a strong net motion for us in one particular direction when we look from our own frame of reference. But real space is not perfectly even. Matter is not spread like a smooth fog. It gathers into clusters and superclusters, filaments and knots. Where there is more mass, there is more gravity. Nearby, concentrations of galaxies can tug on others, slightly slowing the expansion in their neighborhood, or even drawing galaxies inward, like marbles rolling into a shallow bowl. That kind of local motion is expected. In the direction where the Milky Way is moving, however, astronomers saw no obviously enormous cluster that would fully explain the speed they were measuring. There were hints. A general excess of galaxies in that part of the sky. A glow in X-ray observations that suggested the presence of hot gas and large structures, but nothing that seemed large enough on its own to account for such a strong pull. So the questions deepened. Were we seeing the influence of some super-dense concentration of matter, most of it dark and invisible? Or did this motion hint that our ideas about how mass and motion behave on vast scales were incomplete? Astronomer Alan Dressler, thinking about this missing mass, coined a name for the mysterious region, the Great Attractor. The phrase captured both its role and our ignorance. We could measure its influence, but not yet see its heart. Even today, after years of work and many new surveys, the Great Attractor has not completely given up its secrets. We have discovered new galaxy clusters, mapped out strands of the cosmic web, and traced the flow of galaxies with more and more precision. Yet there still seems to be a gap between all the structures we can see and the full strength of the gravitational pull affecting our motion. The Great Attractor remains part discovery, part question mark. What we do know is that this anomaly lies at an enormous distance, on the order of a few 100 million light-years away, roughly a couple of 120 million light-years, in the direction of the constellation Centaurus. It sits within a larger arrangement of galaxies and clusters, often referred to as the Laniakea supercluster, a sprawling region of space in which our own local group of galaxies is just one small inhabitant. In that vast neighborhood, the Great Attractor is not so much a single object as a gravitational focal point. Rather than being one lone monster, the Great Attractor appears to be a region with a higher than average concentration of mass. That mass includes the stars, gas, and dust we can, in principle, detect with telescopes. But it also includes a great deal of dark matter, the elusive form of matter that does not emit or reflect light, yet makes its presence known through gravity. By many estimates, dark matter accounts for something like 85% of all the matter in the universe. In a region like the Great Attractor, its unseen weight may dominate the gravitational landscape. Trying to understand this region feels a bit like assembling a puzzle in dim light. We know that pieces must exist because we can feel the overall pull, but many of the pieces are either faint or hidden behind the glare of our own galaxy. Because the Great Attractor lies in the zone of avoidance, the Milky Way's thick band of stars and dust sits directly in front of it from our point of view, scattering and absorbing much of the visible light that would otherwise reach us from those distant galaxies. Despite that obstacle, astronomers have found ways to look through and around the veil. They use X-ray telescopes to detect the hot gas that surrounds large clusters of galaxies, glowing in high-energy light that can slip through dust. They use infrared instruments to peer into regions where visible light is scattered but longer wavelengths can make it through. They also rely heavily on radio observations, which can pass through the dust of the Milky Way with much less interference. From these efforts, a more detailed picture has started to emerge. The Great Attractor appears to be closely associated with a massive galaxy cluster known as the Norma cluster. This cluster is one of the most densely populated groups of galaxies we know of. A crowded city of stars in deep space, the center of what we call the Great Attractor seems to lie within or near this cluster, where the concentration of both visible matter and dark matter is especially high. The Norma cluster itself is not sitting still. It is moving toward the region of greatest mass at an astonishing speed, roughly 1,340 meters per second, a motion we can detect through small shifts in the light from its galaxies. On even larger scales, the gravitational influence of the Great Attractor extends across hundreds of millions of light years, forming a kind of enormous gravity well. Our own local group, which includes the Milky Way and the Andromeda Galaxy, is being pulled toward this region at a speed of about 370 meters per second, superimposed on top of the general expansion of the universe. Observing all of this is anything but straightforward. You cannot simply point an optical telescope at the coordinates of the Great Attractor and expect a clear portrait to appear. The main difficulty is, again, location. The heart of the region lies behind thick lanes of the Milky Way's disk, in a direction where the sky is crowded with foreground stars and cluttered with interstellar dust. Ordinary light from distant galaxies in that direction is heavily obscured, scattered, and absorbed before it reaches us. To get around this, astronomers have had to be inventive. One of their most powerful tools is the observation of the neutral hydrogen line at a wavelength of about 21 centimeters. Neutral hydrogen gas, which fills and surrounds many galaxies, emits radio waves at this specific wavelength. Sensitive radio receivers can pick up this faint signal even when the galaxy itself is hidden behind dust. Because radio waves are not easily blocked by the dust in our galaxy, they can slip through the Milky Way's obscuring layers and carry information from the far side. Using this method, astronomers can perform blind surveys, scanning large swaths of sky without picking specific galaxies in advance and letting the hydrogen line reveal their presence. It is a bit like turning off the glare of car headlights and listening for the hum of engines instead. You lose the bright, sharp image, but gain access to a different kind of information. In the late 1990s, a group of astronomers began using the Parkes multi-beam receiver, an innovative instrument installed on the Parkes radio telescope in New South Wales, Australia. This receiver's design allowed it to observe multiple points in the sky at once, greatly increasing the efficiency and sensitivity of radio surveys. With it, scientists could systematically sweep through portions of the zone of avoidance, patiently collecting the soft whispers of neutral hydrogen from galaxies otherwise hidden from view. These radio surveys were later combined with new infrared observations from space-based telescopes, which could see through some of the dust that blocks visible light. Together, The data sets built up a richer and more complete map of the hidden structures behind the Milky Way. Gradually, astronomers confirmed the presence of a large fraction of the galaxies they expected to find in that direction. Close to 80% of them have now been identified through these methods, but not all of them. The remaining galaxies, perhaps around 20%, still lie too deeply buried in the densest parts of the Milky Way's disk for current optical or infrared telescopes to confirm. Their light is smothered by overlapping layers of stars, gas, and dust. For now, they remain like pages in a book that are stuck together, their stories hinted at by gravity and by faint radio signals, but not yet fully legible. The region astronomers call the Zone of Avoidance has a name that sounds almost like a warning, but it is really more like a curtain. From Earth, the bright band of our Milky Way stretches across the sky, thick with stars and dust. That glow is beautiful, but it also hides what lies behind it. For a long time, parts of the universe in that direction were simply missing from our maps, as if someone had folded the star chart and tucked away a piece. With new tools, though, that curtain has become thinner. Infrared telescopes can see light that slips between dust grains, and radio telescopes can listen to signals that pass straight through the Milky Way's haze. Together, they act like a soft flashlight in a dark attic, revealing shapes that were always there but never fully seen. Hidden galaxies begin to appear, faint at first and then more clearly, each one a small island of stars that had been quietly overlooked. As astronomers kept filling in those blank spaces, another shape emerged, a colossal structure on scales that are hard to wrap a sleepy mind around. In the vast stretches of space near the southern sky, they found what is now called the South Pole Wall, a sweeping veil of galaxies, dust, and gas that extends for at least 700 million light-years. It is not a wall in the solid sense, but more like a massive ridge in the cosmic landscape, so large that it tugs noticeably on the flow of nearby galaxies and slightly disrupts the smooth expansion of the universe in our neighborhood. Like the Great Attractor, the South Pole Wall has remained largely hidden from casual view because of where it sits. From our perspective on Earth, it lies mostly behind the thickest parts of the Milky Way, in a dim sector of the southern sky. If our galaxy is a glowing lamp hung in space, the South Pole Wall is a faint mural painted on the far wall behind it. It stretches in projection from the constellation Perseus in the northern sky down toward Apus in the far south, but its true shape only becomes clear when you step back and look at the three-dimensional arrangement of galaxies. This structure was brought into focus by an international team led by Daniel Pomered of the University of Paris-Saclay and R. Brent Tully of the University of Hawaii. Instead of just counting galaxies on the sky, they measured distances to around 18,000 of them, reaching out to about 600 million light-years from Earth. By combining those distance measurements with the galaxy's motion, they could see where the cosmic fabric is slightly stretched and where it is gently pulled in. Out of that pattern, the South Pole Wall emerged as a coherent, enormous feature. Even though we cannot photograph it as a single glowing arc, we can feel its presence through gravity. In an expanding universe, distant galaxies naturally move away from us the farther they are, the faster this recessional motion should be, on average. But the region near the South Pole Wall does not quite follow the simplest script. Galaxies that lie between us and the wall are being drawn outward by its mass, so they creep away from us slightly faster than pure expansion would suggest. Galaxies beyond the wall, on the other hand, are held back a little, moving outward more slowly because they are climbing out of its gravitational pull. It is as if the wall is a vast, unseen ridge that nearby galaxies must flow around. In terms of size, the South Pole Wall is comparable to famous structures like the Sloan Great Wall, another huge assembly of galaxies mapped in the northern sky. But the South Pole Wall sits roughly twice as close to us, making it an especially important part of what we might call our local cosmic environment. It is not isolated, either. It appears to be connected to even larger patterns, tying into the Greater Laniakea supercluster that also includes the Great Attractor region. Filaments, clusters, walls, they all link together into something like a three-dimensional web, and our Milky Way is just one thread moving within it. To picture our situation, it can help to imagine yourself in a small boat drifting on a broad river at night. You do not have oars. You can feel the current, but you cannot see all the twists and turns of the water ahead. No matter how much you might wish to steer, the flow beneath you quietly sets your path and speed. In much the same way, our galaxy is carried along by the combined gravitational pull of large structures like the Great Attractor, the South Pole Wall, and others scattered through the cosmic web. We are not falling helplessly into a single point, but we are gently guided by the deep currents of mass around us. To understand those currents better, astronomers, especially in the southern hemisphere, where much of this hidden structure lies, have been patiently charting the nearby universe. One such effort is a project known as the 2-Mass Thule-Fisher Survey, often shortened to 2MTF. Using the Parkes radio telescope, this survey has measured distances and motions for many galaxies, helping to clarify how they are moving relative to the overall expansion of space. It is a bit like dropping thousands of tiny floats into a river and tracking where the water is speeding up, slowing down, or swirling. The work does not stop there. New surveys are coming online with more sensitive instruments. One of them, called Wallaby, uses Australia's CSIRO Square Kilometre Array Pathfinder, usually shortened to ASCAP. This radio telescope is designed to scan wide areas of the sky, picking up the soft 21-centimeter whisper of neutral hydrogen in distant galaxies. With it, astronomers can map the distribution of gas and trace galactic structures more deeply and more completely than before, even in regions overshadowed by the Milky Way's glare. In parallel, the Australian Astronomical Observatory and partners at Australian National University have begun an optical project called Taipan. Instead of gas, this survey focuses on the starlight from mostly elliptical galaxies. By carefully measuring their properties and redshifts, Taipan can reach into more distant and sparsely mapped parts of the universe, adding detail to the skeleton of superclusters and walls that shape the motions we see. As these observations accumulate, they do more than refine a map. They quietly press on our theories. The patterns of motion and clustering in the nearby universe are testing grounds for our understanding of gravity and space-time. Some theorists are beginning to wonder whether the simple mathematical description of space-time we use on very large scales is sufficient, or whether, in certain regimes, we might need to adjust or extend the familiar framework of general relativity. Those ideas are still tentative and carefully debated, but they show how closely our models are tied to what the sky reveals. Running through all of this is the presence of dark energy, the name we give to whatever is causing the expansion of the universe to speed up. On the largest scales, dark energy behaves like a gentle but relentless pressure that stretches the fabric of space-time itself. Galaxies that are not tightly bound to one another drift farther and farther apart, and over time, this drift accelerates. The night sky, on cosmic timescales, is slowly opening outward. For us, that raises natural questions. What does this accelerated expansion mean for galaxies, for superclusters, and for structures like the Great Attractor and the South Pole Wall? If gravity pulls and dark energy pushes, which wins and where? For the moment, the Great Attractor and its neighboring giants still exert a clear gravitational influence on the galaxies around them, including our own. Their combined mass shapes the flows of matter in our region of the cosmos, guiding groups and clusters in long, slow arcs. But as the universe continues to expand, and that expansion accelerates, the balance will shift. The pull of any one region, no matter how massive, will gradually weaken relative to the stretching of space. That leads back to the quiet worry that sometimes surfaces in stories about the Great Attractor. The idea that it might somehow swallow us up, dragging the Milky Way to its doom. In reality, the picture is softer and more subtle. We are not falling into a cosmic monster. We are moving within a network of gravitational valleys, but the floor beneath all of them is being gently pulled apart by dark energy. Far in the future, as the acceleration continues, galaxies that are now slowly drifting toward massive structures may reach a kind of turning point and begin to separate instead. The gravitational bonds that hold superclusters together are expected to loosen over immense spans of time. Large assemblies like the Great Attractor's region and the South Pole Wall will become less tightly knit, their members gradually sliding away from one another as the cosmic expansion outpaces their mutual pull. In that distant epoch, the universe will resemble an ever-widening sea, with galaxies and small groups behaving like islands scattered across a darkening ocean, each one moving slowly away from its neighbors. The Great Attractor, which now acts as a powerful anchor in our part of space, will eventually lose much of its hold over the galaxies around it. Its presence will still be written into the history of their motions, but its future grip will be gentler, fading into the broader drift of an expanding cosmos. Out in the wide, expanding universe, with great walls of galaxies and hidden attractors tugging at us from afar, there is something quietly comforting about turning our gaze back to a familiar light in our own sky. Among all the wandering stars we see at dawn and dusk, Venus is one of the brightest and most haunting. It has been called Earth's twin for its similar size and mass, a sister world wrapped in cloud and silver light. Yet behind that beauty, it is one of the most hostile places we know. For centuries, Venus has been a planet of mystery. From Earth, we see only a smooth, brilliant disk, never its surface. Early on, some people imagined jungles or oceans beneath those clouds. Reality, when we finally learned it, was far harsher. A crushing atmosphere, poisonous clouds, and heat so intense that metal would soften and electronics die in hours. It shines like a lantern in our sky, but up close it is more like an oven sealed shut. In 2021, a spacecraft called Bepi Colombo, built by the European Space Agency, together with the Japanese Space Agency, made a brief gliding visit past Venus on its journey toward Mercury. At the time, the flyby lasted only moments in the grand scheme of things, and the data streamed back quietly into archives. It was only later, in a careful reanalysis published this April, that scientists noticed something unexpected hiding there. Instruments had recorded oxygen and carbon ions slipping away from the planet's upper atmosphere, not gently, but being accelerated to surprisingly high speeds. These are heavy ions, the kind that usually move slowly and are difficult to push around. Watching them being flung outward like this raised a fresh puzzle. What forces are strong enough in that region to pick up such weight and hurl it into space? Some researchers suspect an electrostatic wind, an invisible electric field that can push charged particles along. Others wonder if centrifugal processes linked to the way the plasma flows and rotates around the planet might be lending an extra shove. For now, the exact balance of forces is still not fully understood. Venus has been observed and visited many times before, each mission peeling back a different layer. Early spacecraft, like Mariner 2, were the first to confirm just how extreme the planet really is, measuring surface temperatures far beyond what any human-made probe could endure for long. The Soviet Venera 4 mission sent a probe that descended deep into the atmosphere, tasting the air and revealing that it was dominated by carbon dioxide with clouds of sulfuric acid. Later, orbiters such as Pioneer, Venus, and Venus Express mapped high-altitude winds, electric currents, and tricky structures in the plasma that surrounds the planet. Even with all that, Venus keeps some of its hardest questions close: how it lost its water, why its atmosphere took such a different path from Earth's, and whether there is any way a human presence could survive there, even perched high above the inferno. To understand why this twin world turned out so differently, it helps to linger for a moment in its air. Venus's atmosphere is thick and complex, a towering column of gas made mostly of carbon dioxide, wrapped in global clouds of sulfuric acid droplets. It could not be more different from the nitrogen-oxygen mix we breathe. At the surface, the pressure is about 90 times what you feel at sea level on Earth, as if you were standing almost a kilometer underwater. The temperature hovers around 869 degrees Fahrenheit, hot enough to melt lead. This searing heat is driven by an extreme greenhouse effect. Sunlight passes through the upper atmosphere, warms the surface, and the resulting infrared energy is trapped and retrapped by the dense carbon dioxide, unable to easily escape back into space. Our understanding of this brutal environment did not appear all at once. Mariner 2, flying past in 1962, was the first to show that Venus's surface was not just warm, but incredibly hot, and to confirm that the planet does not have a protective magnetic field like Earth's. Venera 4, arriving a few years later, plunged into the atmosphere and measured its composition directly, finding thick carbon dioxide and clouds of sulfuric acid, along with clues about an ionosphere charged with particles. The Pioneer, Venus orbiter, launched in 1978, spent years circling the planet, gradually mapping different layers of the atmosphere. It revealed weather systems that churn in slow motion, confirmed flows of heavy ions, and helped identify regions where the solar wind collides with the planet's upper air, forming a bow shock and a magnetosheath. Venus Express, sent in 2006, picked up that thread. It carried instruments designed to study plasma and energetic atoms in detail. By measuring how many hydrogen, helium, and oxygen ions were escaping, it built up a picture of how the atmosphere is slowly bleeding into space. Those measurements were crucial for understanding how quickly Venus is losing its air and which parts of it are being lost most efficiently. Into this chain of exploration came Bepi Colombo. In August of 2021, the spacecraft performed its second flyby of Venus, using the planet's gravity to bend its path inward toward the Sunday. During those flybys, Bepi Colombo passed through parts of Venus's induced magnetosphere that had not been explored before. Its mass spectrometer and ion analyzer instruments recorded populations of cold, positively charged oxygen and carbon ions streaming away from the planet, many of them detected at distances of around 6 planetary radii. Among the escaping particles were oxygen ions and carbon ions, with the carbon ions being seen leaving Venus's atmosphere for the first time. This was more than just a curiosity. Heavy ions, like oxygen and carbon, do not usually escape easily. They are massive compared to hydrogen, and it takes a lot of energy to lift them out of a planet's gravity well. The fact that these ions were found so far out, moving at significant speeds, points to a complex and efficient escape process at work, a process driven by the subtle interplay between the solar wind and Venus's unusual magnetic environment. Unlike Earth, Venus does not have a strong, intrinsic magnetic field generated by a churning, metallic core. Instead, it has what is called an induced magnetosphere. When the solar wind, a stream of charged particles flowing out from the Sun, slams into Venus's upper atmosphere, it drapes magnetic field lines around the planet and carves out a kind of comet-shaped bubble. Inside this bubble, solar wind particles are slowed and heated, and electric fields are generated that can accelerate ions along certain paths. The shape and strength of this induced magnetosphere shift with the solar wind's changing moods, sometimes offering a bit of shelter, sometimes channeling energy directly into the upper atmosphere. Bepi Colombo's observations fit into this picture by showing that, in some regions, these electric and magnetic forces can grab hold of even heavy ions and fling them outward. The spacecraft's measurements of ion flows and energies are helping scientists refine their models of how Venus's atmosphere is being eroded over time and how different layers are connected. The more we learn about these escape routes, the more we understand how a thick atmosphere can be slowly peeled away by the Sunday. One of the most sobering insights to come from these studies is the comparison between water on Earth and water on Venus. Many planetary scientists believe that the two worlds may have started with similar amounts of water long ago. If you picture Venus in its earliest days, you might imagine oceans, clouds of water vapor, and rain, just as some models suggest. But being closer to the Sun and lacking a strong magnetic field, Venus was far more exposed to intense solar radiation and to the relentless pressure of the solar wind. As water molecules in the upper atmosphere were broken apart by ultraviolet light, hydrogen and oxygen went their separate ways. Hydrogen, being the lightest element, could easily reach escape velocities and drift away into space. Oxygen, heavier and more likely to be held by gravity, remained behind. Over time, that leftover oxygen reacted with carbon and other elements, contributing to the buildup of the dense carbon dioxide atmosphere we see today, and perhaps oxidizing surface rocks as well. Earth, by contrast, had a strong global magnetic field that deflected much of the solar wind and shielded its upper atmosphere. That protection kept most of its water bound to the planet, making long-lasting oceans and, eventually, life possible. The contrast between the two planets underscores how important magnetic fields can be for habitability. A magnetic shield does not guarantee life, but its absence in a harsh, high-radiation environment can make it very hard for water-rich atmospheres to survive for billions of years. In that sense, Venus offers a kind of warning and a lesson, showing us what can happen when a world like ours is exposed directly to the full force of its star. Each mission that has visited Venus has added a small, essential piece to this larger understanding. Mariner 2 gave us the first confirmation that the surface was extremely hot and that no Earth-like magnetic field surrounded the planet. Venera 4 made the first direct, in situ measurements of the atmosphere, tasting its dense carbon dioxide and sulfuric acid clouds and giving us early data about the ionosphere above. The Pioneer Venus orbiter broadened the view, mapping the structure and dynamics of the atmosphere, identifying heavy ion streams, and tracing the bow shock and magneto sheath. where the solar wind and Venus's air collide. Venus Express deepened that picture, measuring the absolute number of escaping hydrogen, helium, and oxygen ions, and helping to quantify the rate at which the atmosphere is being lost. It showed that atmospheric escape is not a simple, uniform process, but one that changes with solar activity, local conditions, and time. Each dataset is like a snapshot in a long, evolving story. Then Bepi Colombo arrived, with its own instruments and vantage point, cutting through previously unvisited portions of the induced magnetosphere by detecting cold oxygen and carbon ions fleeing from Venus at large distances, including the first clear signs of carbon ions escaping. It revealed that the upper atmosphere is being shaped and stripped in more complex ways than we had appreciated. The induced magnetic field around Venus, shaped like a comet tail, slows and heats solar wind particles, but also creates pathways through which charged atmospheric particles can be accelerated and lost. These observations of ion ejection mechanisms, how particles are picked up, energized, and carried away, are not just technical details. They are vital clues to how Venus changed from a potentially water-rich sibling of Earth into a dry, suffocating world. By untangling the physics of these escape processes, scientists can better reconstruct the planet's past and estimate how much water it once held. Ultimately, understanding these mechanisms is critical for tracing the evolution of Venus's atmosphere, especially the long, slow process through which it lost much of its original water. The quest to understand Venus is not only about measuring how harsh and dangerous it is also about listening for the faintest hints that life, or the ingredients of life, might exist in the most unexpected places. Even inside Venus's fierce atmosphere, wrapped in heat and acid, scientists are quietly searching for the fundamental components that living chemistry might need. High-tech observations from telescopes and spacecraft are tuned to its skies, looking for delicate traces of molecules that, on Earth, tend to appear where life is at work or where conditions might one day allow it. One of the most talked about hints came in 2020, when a team reported signs of phosphine gas in Venus's upper atmosphere. On our planet, phosphine is associated with certain biological processes in low oxygen environments, which led many to wonder whether something strange might be happening high above Venus's surface. Even if that detection is still debated and re-examined, the possibility alone has drawn intense interest. It suggests that by studying Venus's atmosphere carefully, we might learn not only about chemistry, but about the kinds of signatures we should look for when we search for life in other worlds' skies. The challenge, of course, is that Venus is extraordinarily unforgiving. Surface temperatures hover around 869 degrees Fahrenheit, and the pressure is about 90 times what you would feel at sea level on Earth. Any potential life forms would have to be unimaginably resilient to survive there for long. Some scientists imagine that if life exists at all, it would need to shelter high in the cloud layers, where conditions are a little cooler and less crushing, though still filled with droplets of sulfuric acid. Even so, the search continues, guided by the idea that even a negative answer teaches us something important about where life can and cannot take root. To move beyond distant hints and into direct sampling, NASA is preparing 2 missions designed with Venus in mind: Da Vinci and Veritas. Da Vinci will focus on the atmosphere itself, dropping a probe from the upper layers down toward the surface. Along its descent, it will measure gases with great precision, including noble gases and trace elements, from the top of the atmosphere all the way to the lower depths. These measurements will help scientists build more realistic climate models and understand how Venus's atmosphere has changed over billions of years. The Da Vinci probe will also look for molecules that may be precursors to life, or that indicate unusual chemical environments. By seeing exactly how gases are layered and mixed, it can reveal whether there were once conditions more gentle than today's furnace, and whether anything in the present atmosphere hints at habitability, even briefly, in certain regions. These results will be especially valuable when we compare Venus to rocky planets around other stars that sit in similar orbits and may have similar histories. Veritas, by contrast, will spend its time mapping Venus's hidden face. Using high-resolution radar, it will create detailed images of the planet's surface, showing its geology and topography with far more clarity than we currently have. Scientists hope to find signs of past volcanic activity, ancient lava flows, and possible channels or patterns that could indicate where water once moved across the surface. Each of these is an important clue to understanding Venus's deep history and its potential, long ago, to have harbored more gentle conditions. Together, these careful studies of Venus's atmosphere and surface will help astrobiologists refine their models of planetary habitability. Venus is a powerful example, a world that began with strong similarities to Earth, but followed a radically different path. By understanding how two sister planets diverged so dramatically, we can better guess which distant worlds might be truly welcoming and which only look friendly from far away. Venus and Earth are often called sister planets because their basic properties are so alike. They are close in size and mass, and they formed from similar materials in the early solar system. Yet their atmospheres could hardly be more different. Venus's air is made mostly of carbon dioxide and nitrogen, wrapped in clouds of sulfuric acid that form a dense, toxic blanket from top to bottom. Earth's atmosphere, in contrast, is dominated by nitrogen and oxygen, with just enough carbon dioxide and other trace gases to keep the climate mild and varied, supporting a wide range of life. At Venus's surface, the atmospheric pressure is about 90 times higher than on Earth. That is roughly the same pressure you would feel underwater at a depth of about 1,000 yards. The greenhouse effect there is pushed to an extreme. Sunlight filters through the thick clouds, heats the rocky ground, and the dense carbon dioxide traps this heat so efficiently that surface temperatures stay around 869 degrees Fahrenheit. On Earth, the greenhouse effect is gentle by comparison. It maintains temperatures suitable for liquid water and life, but only because many natural processes keep the balance from tipping too far. There are other, quieter differences that matter just as much. Earth spins once every 24 hours and has a stable tilt to its axis, spreading sunlight over the globe in a way that supports seasons, winds, and ocean currents. Venus rotates very slowly and in the opposite direction to most planets in the solar system. One full rotation takes about 243 Earth days. With almost no axial tilt, there are few true seasons, and there is little difference in temperature between day and night. High above Venus's surface, the atmosphere behaves differently still. Thick cloud layers race around the planet in what is called superrotation, circling the globe in about 4 Earth days. These fast winds create a bright, uniform cloud deck that reflects a large fraction of incoming sunlight, giving Venus its striking brilliance in our sky, while at the same time helping to trap vast amounts of heat below. The slow retrograde rotation and this super-rotating atmosphere work together to produce extreme but strangely steady weather patterns. Geologically, both planets bear the marks of volcanic activity, but they express that activity differently. On Earth, plate tectonics slowly recycles the crust. Continents drift, oceans open and close, and carbon is cycled between the atmosphere, oceans, and rocks. This constant movement helps regulate the climate over long periods. On Venus, the surface appears to be dominated by extensive volcanic plains and highland regions, with no clear evidence of moving tectonic plates. Without plate tectonics to steadily release heat, energy may build up beneath the crust until it is released in large, possibly catastrophic volcanic events, resurfacing vast regions at once. Water sits at the heart of why these two worlds diverged. Measurements of the ratio of deuterium, the heavier form of hydrogen, to ordinary hydrogen in Venus's atmosphere suggest that the planet once had a significant amount of water. Over time, the lighter hydrogen would have escaped more easily into space, while the heavier deuterium remained behind, enriching the atmosphere in a way we can still detect. This pattern points to a long history of water loss. Venus's closer distance to the Sun likely drove a runaway greenhouse effect, vaporizing its oceans and feeding a feedback loop that led to the inhospitable world we see now. Earth, meanwhile, orbits at a more moderate distance from the Sun and is shielded by a strong magnetic field. That field helps protect the atmosphere from the direct stripping effects of the solar wind, allowing liquid water to remain on the surface over billions of years. The result is a stable climate window where life could develop and diversify. The contrast between the two planets reminds us that habitability is a delicate combination of many factors, not just size and composition. As we move into a new era of space exploration, several ambitious missions are being prepared to reveal more of Venus's hidden story. The European Space Agency's Envision mission, planned for the coming decade, is designed to provide a comprehensive view of the planet from its deep interior to its outer atmosphere. Envision will build on the discoveries of past missions such as Venus Express, which hinted at ongoing volcanic activity, and will offer a more detailed understanding of both geological and atmospheric processes. Envision will carry a powerful synthetic aperture radar system to map the surface at resolutions down to about 10 meters, revealing fine details of texture, fractures, and possible recent lava flows. A subsurface radar sounder will probe up to roughly 1 mile below the surface, searching for buried structures and layers that cannot be seen from above. A suite of spectrometers will analyze trace gases in the atmosphere, look for volcanic gas plumes, and map the composition of surface materials. In addition, gravity and radio science experiments will use subtle changes in radio signals to study Venus's internal structure and the behavior of its atmosphere on large scales. These measurements will help untangle how volcanism and any tectonic-like processes influence the atmosphere and climate. By seeing how gas is released from the interior, how it moves through the air, and how it might escape into space, Envision will provide critical data to answer long-standing questions about Venus's past and present activity and the dynamics of its thick atmosphere. India's planned Shukrayan mission, led by the Indian Space Research Organization and targeting launch in the early 2030s, will add another important piece. This orbiter will study both the atmosphere and the surface of Venus using a set of advanced instruments. Infrared and ultraviolet cameras will analyze cloud layers, atmospheric composition, and key features of the surface below. By watching how the dense clouds shift and flow and how the atmosphere interacts with the ground, Shukrayan will deepen our picture of Venus's complex climate. One of Shukrayan's main goals is to understand the sulfur cycle on Venus. Sulfur compounds play a major role in the planet's atmospheric chemistry, shaping its clouds, its temperature, structure, and its distinctive yellowish tint. By mapping where sulfur-bearing gases are concentrated and how they change over time, the mission will help clarify how Venus's atmosphere maintains its current state and whether it is still evolving in subtle ways. Together, these missions, Envision, Shukran, Da Vinci, and Veritas, have the potential to transform our understanding of Venus. By combining their data, scientists will be able to build a more complete picture of the planet's geological and atmospheric evolution, from ancient volcanic and tectonic activity to present-day atmospheric escape and chemical cycles. That picture will not only tell us more about Venus's past, present, and possible future, it will also sharpen our sense of what makes a planet truly habitable. By studying Venus in such depth, we improve our models of how atmospheres and rocky worlds behave, and with that, we improve our ability to recognize potentially habitable environments on distant exoplanets. When people dream about the future of Venus exploration, they are not only thinking about orbiters and brief flybys. Somewhere in those plans is a quieter, more daring hope that one day we might send machines, and perhaps even people, into that extreme environment and let them stay long enough to truly know it. The conditions on Venus are brutal heat that can melt metal, pressure that would crush a submarine hull, but advances in technology and a deeper understanding of the planet's behavior keep a small door open in our imagination. In the nearer term, that future belongs to robotic explorers built to endure what no human body could. Engineers imagine landers wrapped in advanced cooling systems, electronics designed to survive temperatures of hundreds of degrees, and structures that can stand under a pressure roughly 90 times that of Earth's sea level. Above them, some dream of habitats floating in the cooler cloud layers, where pressure and temperature are more gentle, shelters that would shield humans from the heat and acid and give them a window onto the turbulent yellow sky. Inside, life support systems would quietly recycle air, water, and resources, allowing longer stays and more thoughtful science rather than quick, desperate snapshots. Pushing toward Venus is not only about visiting our nearest planetary neighbor, it is also a way of stretching our abilities to their limits. Every challenge the planet presents, its atmosphere, its heat, its corrosive clouds, forces us to invent new materials, new systems, and new strategies. The lessons learned there would echo outward, helping us design missions to other harsh worlds in our solar system and to extreme environments we have not even named yet. From that vision of explorers braving the edge of a hostile world, it is a small step to another frontier, not outwards to planets, but inwards to the smallest scales of reality. Imagine a place where the usual boundaries feel less solid, where the fabric of the universe is tested and stretched, not by fantasy, but by carefully controlled experiments. That place exists, not in orbit or on a distant moon, but deep underground beneath the border between France and Switzerland. There, beneath quiet fields and gentle hills, lies the largest machine humans have ever built, the Large Hadron Collider. It is a marvel of engineering and patience, a circular tunnel buried in rock, filled with magnets colder than deep space, and instruments sensitive enough to catch whispers of particles that live for only a fraction of a second. It is also a monument to curiosity, a reminder that our urge to understand the universe goes all the way down to its tiniest building blocks. Some people hear about the energies reached in this machine and wonder whether it might open portals to other dimensions, like something from a science fiction story. In reality, what it opens are windows of understanding, brief moments when particles collide at such high energies that theories about extra dimensions or hidden particles can be tested. At CERN, the European Organization for Nuclear Research, ideas about space, time, and reality are woven together with the results of these high-speed collisions. It is not a story of magic gates, but of careful measurements that might reveal whether the universe is stranger and more layered than it first appears. CERN itself sits in a serene landscape where mountains watch from a distance and vineyards and villages follow the rhythm of the seasons. Below that calm surface, in tunnels and caverns, scientists and engineers from around the world work side by side. Founded in 1954 to bring nations together through shared scientific effort, the laboratory has grown into the largest particle physics center on Earth. More than 10,000 minds from over 100 countries come here, in person or through collaborations, to gently push against the limits of what we know. At the heart of this place, deep underground, is the Large Hadron Collider, often shortened to LHC. It is a circular ring about 17 miles around, a vast loop in which beams of tiny particles, usually protons, are accelerated to speeds very close to the speed of light. Powerful magnets guide them around the ring again and again, adding a little energy with each lap until they are finally steered into one another. When they collide, the energy concentrated in that tiny point recreates, for an instant, conditions similar to those that existed just moments after the Big Bang. In those instants, the fundamental ingredients of the universe reveal themselves in patterns of tracks and flashes, recorded by enormous detectors. The LHC is both a machine of brute force, slamming particles together at enormous energies, and a machine of exquisite precision, measuring the slightest deviations in how those particles behave. Every collision adds a little more detail to our picture of the world at its smallest scales. Much of this work is framed by what physicists call the Standard Model of Particle Physics, a theory developed during the middle of the 20th century. The Standard Model describes a zoo of particles, quarks, leptons, and various force carriers, and explains how 3 of the 4 fundamental forces behave. It has been remarkably successful, predicting particles that were later found and matching countless experimental results. And yet, it is clearly not the full story. It does not include gravity in a natural way. It cannot explain dark matter, and it leaves several deep questions unanswered. The energies reached at the Large Hadron Collider provide a rare testing ground for ideas that go beyond this incomplete picture. One of these ideas is supersymmetry, a theory that proposes that every known particle has a heavier partner, a kind of shadow twin. If these superpartner particles exist, they could help explain mysteries like the nature of dark matter, which seems to make up much of the universe's mass while remaining invisible to our telescopes. The LHC looks for subtle signs of such partners in the debris of its collisions, unexpected tracks, missing energy, or patterns that do not fit the Standard Model's predictions. Another line of thought being probed touches on string theory, a framework that tries to bring gravity and quantum mechanics together. In string theory, the particles we see are not point-like dots, but tiny vibrating strings, and different vibrations appear to us as different particles. The theory often requires extra dimensions of space beyond the 3 we move through in daily life, dimensions that might be curled up so small we cannot see them directly. The energies and densities reached in the LHC's collisions may offer ways to test some of these ideas. If extra dimensions exist in certain forms, or if strings and their related particles leave distinct fingerprints, they could show up as new particles, or as small but telling deviations from what the Standard Model predicts. In that sense, each collision is a quiet question posed to the universe. Is there more here than we thought? Are there deeper layers hiding beneath the ones we know? The Large Hadron Collider has already changed our understanding once, with the discovery of the Higgs boson, a particle linked to the mechanism that gives many other particles their mass. That discovery confirmed a missing piece of the Standard Model and showed that this giant machine could indeed reach into the heart of fundamental physics. Now, as it continues to operate, and as upgrades increase its power and sensitivity, it keeps searching for hints of supersymmetry, signs of dark matter, or subtle traces of extra dimensions. Even when the answers are no or not yet, the results guide theorists in refining their models. In this way, the LHC is less a portal and more a mirror held up to reality, reflecting back the universe's true behavior at energies we cannot reach in any other way. Just as future missions to Venus will test our assumptions about planetary habitability, experiments at CERN test our assumptions about the very nature of matter and space. Both kinds of exploration, one among the planets, one among particles, remind us that there is still so much we do not know, and that gently, patiently, we are learning to ask better questions. When people talk about the Large Hadron Collider opening portals, the word often drifts straight into science fiction. Our minds jump to glowing doors in space, shortcuts to other universes, or tunnels through time. In popular stories, a portal is a doorway you step through. In high-energy physics, the idea is quieter, stranger, and much more subtle. Scientifically, when physicists speak of something like a portal, they are usually talking about very small, very brief phenomena that might appear in particle collisions. One possibility, predicted in some versions of string theory and related models, is the creation of microscopic black holes. These would not be monsters in the sky. They would be tiny, short-lived objects that form for a heartbeat of time when particles collide at enormous energies, then evaporate almost instantly. If they appear at all, they would pose no threat to our world, despite the loud headlines that sometimes try to suggest otherwise. In movies, portals are doors to alternate realities. Inside the collider, they are more like narrow windows into conditions that barely exist in the natural universe anymore. When the proton beams collide, they briefly recreate densities and energies similar to those in the first instance after the Big Bang. In that flash, new particles can emerge, including ones that might carry hints of extra dimensions or new forces. By carefully analyzing the spray of particles that rush out from these collisions, scientists can test ideas that would otherwise remain only on paper. This is what people mean when they say the Large Hadron Collider could open new dimensions of physics. It is not that we walk through into another world, but that our understanding expands. Each pattern of tracks in a detector, each tiny imbalance of momentum, is a clue that either supports a theory or gently pushes it aside. With its ability to probe energies never reached before in a laboratory, the collider acts like a giant microscope, one that does not magnify a leaf or a cell, but the very fabric of reality itself. Particle physics is always in motion. Every time the collider runs, it adds something to the story, a new limit on how heavy a particle can be if it exists at all, a fresh test of how forces behave, or in rare, wondrous cases, the first glimpse of something we only suspected was there. One of the most famous of these moments came with the discovery of the Higgs boson, a particle tied to the mechanism that gives many other elementary particles their mass. The Higgs boson was first observed in 2012 by teams working on two large experiments at the collider. Its existence had been predicted decades earlier, but seeing it directly confirmed a crucial part of the Standard Model and earned the Nobel Prize in Physics in 2013 for the theorists who laid the groundwork. People sometimes call it the God particle in the media, but physicists tend to prefer its quieter name. For them, the beauty lies not in drama, but in the way its presence completes the puzzle of how particles acquire mass. Recently, the CMS collaboration at CERN has taken an important step toward openness by making the detailed data and tools behind their Higgs analyses publicly available. This includes the complex software used to search for the particle and to tease its signal out of a background of many other processes. The resulting statistical description, the likelihood function that encodes how well different hypotheses match the data contains on the order of 700 parameters. It is a kind of multidimensional landscape that captures the richness of the measurements in a way that is hard to visualize, but essential to precision. By sharing these tools and data, CERN and its collaborators invite scientists around the world to explore the details for themselves, to check the results, and to build new ideas on top of them. This openness turns a single discovery into a shared resource, strengthening the global scientific conversation and making it easier for independent groups to test, refine, or extend what has already been found. The Higgs boson is only one chapter. CERN has also played a central role in other deep investigations, many of which sound almost as dreamlike as fiction when you first hear them. One long-running effort focuses on antimatter, the mirror form of ordinary matter in which charges are reversed. In theory, the Big Bang should have produced matter and antimatter in equal amounts, yet the universe we see is overwhelmingly made of matter. Somewhere along the way, a small imbalance must have emerged. Experiments such as ALPHA have managed to produce and trap anti-hydrogen atoms, antimatter counterparts of ordinary hydrogen, for long enough to study their properties. By comparing how antimatter responds to electric and magnetic fields, and even to gravity, with the behavior of normal matter, scientists hope to find tiny differences that might explain why one kind dominates the cosmos. Another line of research explores a state of matter called quark-gluon plasma, believed to have filled the universe in the very earliest moments after the Big Bang. In this state, quarks and gluons, which are usually confined inside protons and neutrons, move freely in a hot, dense soup. By colliding heavy ions, such as lead nuclei, at incredible energies, experiments at the Large Hadron Collider can briefly recreate this plasma. Detectors such as LHCb and others then study how particles emerge as the plasma cools and condenses back into ordinary matter. These studies reveal the behavior of the strong force, the fundamental interaction that holds atomic nuclei together. Each of these achievements demands exquisite coordination. Hundreds of scientists, engineers, and technicians must design detectors, build electronics, maintain cryogenic systems, analyze data, and develop new methods. All of this happens at the edge of what our current technology can handle. Magnets cooled to temperatures colder than deep space, sensors that can withstand floods of particles, and computing systems that sift through enormous amounts of information to find the few events that matter most. After wandering through why the collider exists and what it has shown us, it is natural to wonder how, exactly, it works. The process begins far more simply than you might expect. The protons that race around the ring start life in something as ordinary as a bottle of hydrogen gas. From that gas, electrons are stripped away, leaving bare protons behind. Those protons, no larger than subatomic specks, are then guided into a chain of smaller accelerators. In each stage of this chain, the protons are nudged to higher energies, circling smaller rings before being passed to the next. By the time they reach the Large Hadron Collider itself, they are ready for the final push. Inside the main ring, powerful radio frequency cavities give the particles repeated bursts of energy, while superconducting magnets bend their paths and keep them on course. In the most recent operating periods, each beam has been accelerated to energies around 6.8 tera-electron volts, often written as 6.8 TeV. When two beams moving in opposite directions collide, the total collision energy reaches about 13.6 tera-electron volts. These numbers can sound abstract and intimidating, so physicists sometimes use a gentler analogy. The kinetic energy of 1 tera-electron volt is roughly comparable to the energy of a flying mosquito. 6.8 tera-electron volts is like the energy of about 6.8 such mosquitoes. The difference is that in the collider, all of that energy is packed into a single proton, a particle with a diameter of about 1 femtometer, which is a millionth of a billionth of a meter. By comparison, a mosquito might be about 1/4 of an inch long. If you imagine a proton scaled up to the size of a pea, the mosquito in that same scale would be as large as a skyscraper. Yet the energy of the moving skyscraper is somehow concentrated into the tiny pea. When those peas collide, the energy is so intense in such a small volume that new particles can appear. To make meaningful measurements, the beams must not only be energetic, but also extraordinarily stable. Protons need to be bundled into tight packages and focused to cross at precise points inside the detectors. This squeezing of the beams is controlled by an elaborate array of magnets distributed around the ring. Small changes in their currents can move or shape the beams, so they must be tuned with great care to keep the particles on track. When the beams are dense, well-focused, and circulating steadily, physicists say that the collider has reached a state of stable beams. Reaching this state at the record energies of the latest runs is a milestone each year. In 2024, the machine entered another season of data, taking part of what is known as Run 3. During this period, it is planned to provide many months of proton-proton collisions at energies of about 13.6 tera-electron volts with higher luminosity than before. Higher luminosity means more collisions per second, and more collisions mean more chances to see rare processes. Later in the same running period, the collider will switch to lead-ion collisions, creating the hot, dense conditions needed to study quark-gluon plasma in detail. Each of these modes, protons and heavy ions, offers a different window into fundamental physics. Even within a single run, important results continue to emerge. The ATLAS experiment, one of the major detectors on the ring, has recently achieved a milestone by measuring the width of the W boson, the particle that carries part of the weak nuclear force. The width is related to how quickly the boson decays and how uncertain its mass appears in measurements. ATLAS found this width to be about 2,202 mega-electron volts, a value that fits well with the predictions of the Standard Model. Each such agreement tightens the net around possible new physics, showing where there is room for surprises and where existing theories hold firm. Meanwhile, the LHCb collaboration, with its special focus on particles containing beauty and charm quarks, continues to explore the subtle imbalance between matter and antimatter. By studying neutral D mesons and neutral strange B mesons and how they transform and decay over time, LHCb is uncovering new details of how charge parity symmetry is violated. These tiny differences in behavior between matter and antimatter are thought to be linked in ways we are still unraveling, to why the universe ended up dominated by matter rather than annihilating itself completely in a flash of light. All of these efforts searches for new particles, precision measurements of known ones, studies of matter under extreme conditions take place in the same carefully tuned environment. The Large Hadron Collider is not just a loop of metal and magnets. It is a place where some of the most delicate questions we can ask about reality are posed, one collision at a time, and where the universe answers in faint traces etched into detectors deep beneath the ground. Deep inside the data from the Large Hadron Collider, there are particles that behave almost like tiny, flickering thoughts appearing as one thing, then quietly shifting into their mirror version and back again. One of these is the neutral D meson, built from a charm quark and an up antiquark. In the strange language of quantum mechanics, it does something that feels almost like a magic trick. It can spontaneously transform into its own antimatter counterpart and then return to its original state. This back and forth, called mixing, has been known in theory for some time, but recent analyses of the first two running periods of the collider have captured it with a new level of precision. By watching how often the neutral D meson becomes its antiparticle and how those transformations unfold over time, physicists can search for tiny imbalances between matter and antimatter. These imbalances are known as charge-parity, or CP, violations. If they are present in the D meson system in just the right way, they could offer clues to one of the deepest questions we have: why the universe is filled with matter rather than having matter and antimatter completely cancel each other out. A similar story plays out with another particle, the neutral strange B meson, which contains a bottom antiquark and a strange quark. This meson also has the ability to oscillate between matter and antimatter versions, and when it decays, the patterns in its decay products can show time-dependent CP violation. Recent measurements have seen such effects with statistical significance beyond the usual threshold used in particle physics to call something a clear observation. That means these are not just hints or faint suggestions. They are solid signals, captured carefully in the data. These results confirm aspects of behavior that theorists expected, but they do more than that. They sharpen our tools and open new paths. As the collider now operates with higher luminosity, producing more collisions per second than before, future data will let scientists refine these measurements even further. In those refinements, there is space for surprises. A small deviation from the predictions of the standard model could be the first sign of new physics, perhaps a link to dark matter, or a deeper explanation of why the scales tipped in favor of matter in the early universe. Around the Large Hadron Collider, in the wide world beyond the tunnels, stories and myths often grow like mist. It is easy, from a distance, to imagine that something so powerful must be dangerous in ways we barely understand. So part of understanding this place is gently separating what is truly happening underground from the exaggerated tales that sometimes rise above it. One common fear is that the collider might accidentally create a black hole large enough to swallow the Earth. In reality, if microscopic black holes are created in these collisions, something that would itself be an extraordinary discovery, they would be unimaginably small and vanish almost instantly. A process predicted by Stephen Hawking, known as Hawking radiation, tells us that such tiny black holes lose their energy and evaporate extremely quickly. The energies reached at the collider are enormous by laboratory standards, but still much smaller than the energies naturally carried by cosmic rays, which have been colliding with Earth's atmosphere for billions of years without causing any harm. Another dramatic claim suggests that the collider could open portals to other dimensions or trigger catastrophic natural disasters. These images are vivid and make for gripping fiction, but they are not supported by any scientific evidence. The whole purpose of the collider is to study particles and forces under controlled conditions, to test precise predictions of theories like the Standard Model, supersymmetry, or certain versions of string theory. It is not designed to tear open reality, but to listen more carefully to how reality already works. CERN, the laboratory that runs the collider, operates under strict safety protocols. Experiments are reviewed, risks are assessed, and results are shared openly with the global scientific community. If there were any realistic danger, it would show up in the same equations and models that physicists use to design and interpret their experiments. Instead, those models show that the conditions created in the collider are not unique. They are milder than events that happen naturally throughout the universe. Stories about secret experiments or supernatural phenomena at the collider also miss what CERN actually is: a transparent, collaborative scientific institution. Research results are published in open journals, datasets and software are increasingly shared, and collaborations span continents. The control rooms and tunnels may feel like something from a science fiction set, but the work they host is grounded in careful measurement, critical review, and public documentation. From this steady, factual base, physicists push into some of the most adventurous ideas we have about the universe. When they talk about higher dimensions, for example, they are not sketching fantasy worlds, but exploring theories that try to bring gravity and quantum mechanics into the same framework. In our everyday life, we move through 3 dimensions of space and 1 of time. String theory and superstring theory suggest that reality might, at a deeper level, have more than these 4. In some versions, there could be as many as 10 or 11 dimensions, with the extra ones curled up or hidden at scales too small for us to see. In these theories, the particles we think of as tiny points are instead one-dimensional strings vibrating in a multi-dimensional space. Different patterns of vibration show up as different particles. The existence of extra dimensions could help resolve tensions between our best description of gravity, general relativity, and our best description of the quantum world. It could also offer explanations for puzzles, like why gravity seems so weak compared to other fundamental forces. Researchers at CERN look for signs of such dimensions indirectly. One strategy is to search for new particles that would only exist if extra dimensions are real, or for missing energy in collisions that might indicate particles slipping into directions we cannot perceive. Another is to look for tiny deviations in how known particles behave at very high energies. If microscopic black holes were ever produced, their decay patterns might also carry the imprint of extra dimensions. The search for higher dimensions is not only a philosophical quest. The tools and technologies developed to probe these possibilities lead to advances in many other fields. Detectors that can spot extremely rare signals, electronics that can process trillions of events, and analyses that sift meaningful patterns out of vast data streams. All of these feed back into areas such as medical imaging, materials research, and even quantum information science. As the questions become more subtle, the instruments required to answer them become more refined. Looking ahead, CERN is also preparing a new generation of experiments to chase particles that are even more elusive than those currently studied. One of the most intriguing initiatives is called the Search for Hidden Particles, often shortened to SHIP. This project is designed to hunt for so-called ghost particles, hypothetical particles that interact so weakly with ordinary matter that they could easily slip through our detectors unnoticed. Unlike the head-on collisions inside the Large Hadron Collider, the SHIP experiment will use a fixed target setup. A powerful beam of particles will be directed onto a dense target, producing a cascade of secondary particles. Most will decay quickly or be blocked, but if hidden particles exist, some may travel quietly through shielding and leave faint, telltale signs in a downstream detector. Because of its design, SHIP is expected to be far more sensitive, perhaps up to 1,000 times more sensitive, to certain kinds of weakly interacting particles than existing experiments at CERN. These ghostly particles are not just curiosities. They are candidates for dark matter, or could be connected to the dark energy that seems to drive the universe's accelerated expansion. Detecting them, or even placing tight limits on their properties, would reshape our understanding of the cosmos. The discovery of such particles would ripple through many branches of physics, forcing us to rewrite chapters of textbooks and inspiring new generations of questions. Alongside SHIP, plans are being laid for a possible future circular collider, a much larger ring that would build on what the LHC has taught us. If constructed, this new collider could begin operations around the middle of the 21st century. With a greater circumference and higher energies, it would push particle collision technology to new heights, allowing deeper probes into the structure of matter and the behavior of forces. Together, projects like SHIP and the future circular collider sketch a quiet but extraordinary future. From refining the details of meson mixing and CP violation, to searching for hidden particles and testing the existence of extra dimensions, they promise to take us further into the fine grain of reality than we have ever gone before. Each new measurement, each carefully recorded collision, is a small step in a much larger journey, a journey in which the universe reveals itself, not all at once, but in countless small flashes of understanding, one experiment at a time.